I'm a curious man with some curious genes. I get that from my dad. I'm not far from the tree. I feel like I'm a butterfly, sting like a beamer. I ain't features, done my running around with my head in the clouds, spinning lost and then found. When they woke up and frowned, tell myself I'm the man. I was right to be left. Now I'm back to myself. To keep on holding you from everything you want. I can see you want to get you want. Who am I to? Who am I?
Looking right, left, going straight. Don't know where to go, wanna hide away. Reflecting myself. You are no good for me. So dangerously, am I?
Hello everybody, welcome to class this afternoon. To our 8th live stream, if you can believe it. I was kind of shocked myself when I was going and looking through all the different live streams that we've done so far for CTI 140 this semester, and now we're on number 8. Pretty incredible. You know, I was just kind of trying out live streaming and stuff as a little test this semester, and I've kind of enjoyed doing it, and I think it seems to be getting some pretty good results with you all. So, yeah, I'm glad we're all kind of having fun with it. Today we're talking about virtualizing memory. Hey, Jorge, good afternoon to you too. Good to see you. Today we're going to be talking about virtualizing memory in just a moment. Before we get into that, I wanted to mention the issue that I posted about in the announcement this past Friday with the VMware Workstation Pro and the blacklisting with the Windows Update. So what is happening, it seems like as of the October 9th Windows update is with VMware Workstation Pro 15. It is blacklisting that in the Windows Compatibility Assistant. So there are a few options for what we can do with that. One is to, and probably the easiest option is probably to roll back Windows updates. The easiest thing would probably be to roll them back prior to the September 26th release. VMware is offering a VMware Workstation Pro 15.5 patch that some people are having some success with as well. So you can find that, I think, on VMware's website. Although I've read some mixed reviews on that, I think the easiest thing probably is the rollback. Or if you haven't updated yet, if you have auto updates turned off, just waiting to update a little before, for a few weeks, then that's probably a good idea as well. But that's basically what's going on there. It's not an issue with the software per se. It's what Microsoft has done with the Compatibility Assistant, and it's blacklisted it in the Compatibility Assistant. So it's an easy way for them to get something not to run on a Windows 10 system, I would guess. Could have something to do with some Hyper-V stuff coming up. Maybe, maybe not. Who's to say? But you do have a few options with how to work with that. And for modules outside of the current one, when we get into the VMware vSphere module starting next week, then I'm giving you some options as to how you approach those. Because I've done the struggle for you to figure out how to do VMware vSphere ESXi in VirtualBox. So that was a bit of a challenge, but we got that figured out, and those videos are in the first vSphere module now. But today we're talking about virtualizing memory. When you think about 20 years ago, the concept of computer memory was isolated in a few pockets of people who, in some way or another, were involved with computers. We weren't even talking about it in terms of memory at that time. If you all are probably old enough to think back to that. Everything was RAM. We called it RAM instead of memory, as we tend to term things now. RAM being random access memory. And RAM was kind of thought of and treated like another storage device, like a disk. And it was a whole lot faster type of disk that you could access data in memory with a more flexible model than accessing data from standard hard drives and disk storage devices. So system memory sizes were, when we also think about it, back in those days, system memory sizes were also much, much smaller than what we deal with today. Now we're talking about things in terms of gigabytes, 8, 16, 32 gigabytes. But back 20 plus years ago, we were talking about things in terms of megabytes and even kilobytes for RAM and memory. So when you think about RAM, or when you think about memory, and how we have it today, this kind of goes to kind of the stuff that we've been talking about week over week when it comes to, like better, more efficient hardware making better virtualization possible. So last time we talked about virtualizing the processor and how that kind of worked. And memory, like the processor, is a crucial part of the virtual machine. Unlike the CPU, memory is usually the resource that is consumed the fastest. When we get into using up our memory, it goes really, really quick. I was making some demonstrations last week for some future modules in the course, and I actually ran out of memory doing the virtualization stuff. I had too many windows open, and then I was trying to make a new virtual machine and then start my virtual machine, and I had actually run out of memory. I was trying to do too much. What hypervisors do is hypervisors kind of abstract memory by handling data blocks between the servers or your host computer's physical memory and what has been allocated to the virtual machines. And then the management of memory resources by both the hypervisor and the administrator, you essentially, is important to the effective use of these physical resources. So that's what we're going to get into today. So in saying that, memory is just storage. Just really fast storage. So we can kind of think of virtualizing memory in the same way that we would kind of think of virtualizing a hard drive. And we kind of talked briefly about how we would do both of these in the past. But memory is a computer's workspace. When an operating system boots up, certain regularly used routines and processes are loaded into memory and they stay there. You at this point, you've all taken certain classes, in your hardware classes and in your operating system classes. You've talked about these things and you know how they work. As programs are executed, these routines, they're copied into memory, so that things from the memory can transfer into the processor, and then the processor can process them, send them back to memory, and then out to the display or back to the hard drive, all that kind of fun stuff. And these routines, they're copied into memory as well as so it can kind of speed up execution, and you can have quick access to the processes for reuse. When programs work on information, that data is also moved into memory, so that all calculations can be processed by the CPU. So when we think about memory in that sort of way, those are the two kind of things that memory. Set my notes down on my arrow key. Sorry. Those are the two big things that we can kind of think about using our memory for when we're thinking about our memory in general. Kind of caching data in that sort of way, so things are quick. Speed of execution, quick access for reuse, and then that sort of scratchpad type of thing where we have the data loaded into memory so that we can do the calculations on it. Virtual machines use memory in the same way. Really more than any other resource, memory is the one with the largest impact on how well or how poorly the virtual environment performs. similar to CPU virtualization, the hypervisor abstracts memory by using the physical host's memory on behalf of the virtual machine. So when we think about it, that sort of, if you think back to when we talked about this the last time, it's virtualizing it on behalf of the virtual machine, but it's also different from what we talked about the last time with virtualizing CPUs. With memory for a virtual machine, and if you remember back to last week, the processor just kind of slices out sections of time. It kind of treats it lets the virtual machines kind of use the processor in the host machine, kind of like a timeshare down in Florida. It kind of communicates with other processes going on the host machine. Says, hey, we got some data to process. Can we process this really quickly? On the contrary, virtual machines actually, with the hypervisor actually maps virtual memory blocks to physical memory and uses address translation to translate tables to keep track. So there's actual physical memory that actually maps directly to the virtual memory blocks that the hypervisor is creating. And these tables are part of the hypervisor's overhead. These tables are one of the things that the hypervisor manages. So this hypervisor, it's a really busy boy. It's gotta schedule all this time for processing, and it's gotta manage all these memory. It's gotta manage these virtual memory to physical memory address translations, in addition to all the other hardware that it virtualizes and manages. The hypervisor is super busy. So memory blocks, so we have these blocks of memory that are kind of sectioned out. We can also call them memory pages. They're typically moved around in uniform sizes. We can think of, with typical memory page size, we're looking at around 4 kilobytes. When memory blocks need to be freed up so newer information can be loaded, the older, less recently used blocks are written to disk. So the disk acts kind of as an extension of that physical memory. So if you're familiar with the idea of a page file on your host machine, if you've been working with in some of your operating system classes or maybe some of your server administration classes with the concept of page files. We have page files here in virtualization. And it is that extension of the physical memory onto the disk by copying pages to the disk that are being less used. And so we can kind of see in the illustration that we have here on the screen, this is kind of a simplified version of how data kind of travels through. Our processors have a physical memory called a cache. And if you remember back to like hardware classes and such, there are different levels to that cache. So data goes from the CPU to the cache to the memory and to the disk. Well, one of the problems with this sort of disk storage type of stuff is that it's a whole lot slower. So paging is a really expensive process. It takes a lot of time in general because things are writing from the disk and reading to the disk. That sort of I/O type of process, especially dealing with standard hard drives, is slow. And as we've already mentioned, memory is the resource most likely to be scarce. So we're going to end up with a situation where we're having these kind of problems a lot. So it's good to kind of overbuild host machines or servers that you intend to put virtual machines onto with a lot of RAM in them, with a lot of memory in them, so that you can kind of avoid some of these issues, so that you have plenty of memory for all of the virtual machines to be able to utilize. Now we'll talk briefly about configuration here. Memory can be added or subtracted. It's kind of an odd wording to that line there. I'm not sure what I meant by memory can only be added or subtracted. Because, those are about the only things that you're going to do with memory. You're going to either add some or you're going to take it away. Depending on the operating system, you can hot add memory. And then subtraction requires a reboot. It's similar to how we were talking about processors last week. Adding more processors. You can hot add more processors, but if you wanted to remove processors, then you would have to take the VM offline. It's a similar thing here. You can always ramp things up, but it's a whole lot more difficult to kind of slam things into a wall to try to slow them down. So ideally, when you're looking at adding memory to a virtual machine in this sort of way, one of the things that you could kind of do is you could under-provide memory to your VM. We got the memory screen from VMware Workstation Pro as a graphic here on the screen. It shows you the base recommended, a recommended memory, and a maximum recommended. And you could actually start toward the lower recommended minimum and add a little bit, hot add a little more memory if you need some as the machine's running, so as to not overwhelm all of your resources all at once, and then you're kind of being economical with your resources for the virtual machine. You're kind of giving it the amount of memory that it needs to do its job. So we're going to want to configure it with just enough to do the job that it's been assigned. Because too much is, you're wasting it if you're using too much. Looking at memory overhead. So of course the hypervisor is running on the host system. So it's going to require some memory for its own needs. Because it's got to do things as well, like it's got to perform tasks. It's got to, send messages to the processor. It's got to, do the memory mapping. It's got to do a whole bunch of different stuff. And in order to do that, it's got to be able to use some of the memory itself. Now, as that technology is improved, the amount of overhead that the hypervisor needs to be able to do its job has shrunk dramatically. And then we have other VMware or other VM memory optimizations that have helped overall consumption. But, to think about it, in the past, we could see like upwards of 20% of the memory of the host would be dedicated to the hypervisor for the purpose of doing its job. And now it's much, much less. I want to talk briefly about memory ballooning. So what ballooning does is ballooning reclaims unused memory from a virtual machine when it is needed somewhere else. So you can kind of think of ballooning this way. In order to take the physical memory back from a virtual machine, the pages that are in memory need to be kind of flushed back to a different storage device. So, it could be the paging area of the disk. It could be, one or two other things. But most often, what we're looking at is the paging area of the disk. So essentially what we get in ballooning, as we kind of see in the graphic, is we get all this memory in the balloon. The host machine says, I need more memory. I need to be able to run. I'm the host. If the host doesn't have its memory, we all go down. So I need to be able to take this memory back from the virtual machine. So we just need to deflate that balloon onto a page file, onto the disk. And then once that memory from the host machine is kind of freed up, then the hypervisor can bring that page file back from the disk and reinflate the balloon. So this actually gets us, allows our hypervisors to physically or to facilitate memory overcommit. And when we look at memory overcommitment, essentially what memory overcommitment is the ability to allocate more virtual memory on a host than physically exists. I think I have some more. Yeah, here we go. Memory overcommitment allows virtual machines to be allocated more memory than is in the physical virtualization server or host machine. Here, we have this graphic here. In the graphic, the host has 16 gigabytes of memory, but the three virtual machines have allocated a total of 24 gigabytes of memory. So we can utilize memory overcommitment. It's a really powerful virtualization technique, but it's kind of important to understand the memory usage characteristics of your virtual machines in order for this to be effective. because really idle virtual machines or VMs with more memory allocated than they use, that's what allows the hypervisor to manage that memory across multiple virtual machines. So you have a better consolidation ratio, which, we've talked about consolidation in the past. So we can have these virtual machines that all have 8 gigabytes of memory, but if they're not all using 8 gigabytes of memory, then the hypervisor in turn is kind of juggling the memory. It's taking these 16 gigabytes of memory and it's kind of playing, I guess, kind of shell game with it. It's like, oh, virtual machine A needs some memory, let's put some over here. Virtual machine B needs some memory, let's put some over here. Virtual machine C needs some memory, let's put some over here. As long as any of the virtual machines are not outpacing that 16 gigabytes that the host machine has, then you're fine. And you can actually run in certain environments, you can run a 2-to-1 overcommitment ratio, where you have double the amount of virtual memory in across all of your virtual machines than you actually have in your physical machines. Which is pretty fancy, if you ask me. We also have Paige Sharing. Paige Sharing, it's sort of analogous to data duplication in that sort of way. What we're doing is we're duplicating pages in different VMs that are mapped to the same page in physical memory. So this is a technique that storage vendors often use to reduce data blocks and save disk space by storing only one copy of a duplicated data block. So if you have a data block that is kind of the same between different virtual machines, as kind of illustrated in our graphic here, we can put them into a shared data block on our physical memory. So it's kind of basically reading the same memory file for all of our virtual machines. We have one, and it'd be kind of like it'd be kind of like if you had 3 video game consoles and one disc between all of them, sorta. But in that sort of way, we can use that to reclaim 10 to 40% of our physical memory, which can help us with that help prevent us from that overcommitment stuff, help us not have to do any of that ballooning that we talked about. That's a big memory savings there. And so Paige Sharing has a lot of good impact for us when it comes to the savings that we can get in virtualization for our memory. Taking that identical memory block that's identical between the virtual machines and having it stored in one location on our physical memory and just shared between the virtual machines. And so that's all of the content that I have for you all today. To just run this down really quickly, remember that memory is a key resource for effective virtualization. Again, if you want to overbuild your host device, your virtualization server, or your host for virtual machines, one thing that you want to do is you want to overbuild it with memory. We have a lot of memory optimizations that make virtualization more effective. We had talked about memory overcommitment, memory ballooning, page sharing. There's also memory compression that we didn't talk about. Let's see, I think I might have put that in my notes. Let me look here. The goal of compression is basically to defer swapping out pages to a disk, since it's more time expansive and resource consuming. So we compress our memory instead of doing page swapping and all that sort of stuff. And the hypervisor actually reserves a portion of memory to use as a compression cache. So when it determines that a paging needs to occur, it can examine the pages with algorithms to see the viability of compression. And then if the pages can be compressed, it compresses them instead of paging them out to the disk for efficiency purposes. So there's memory compression for you in a nutshell. And memory optimizations in that sort of way help drive higher consolidation ratios and lower costs of optimization, or lower costs of virtualization, rather. So that's what I've got for you for today. Thank you for coming to the live stream. That's kind of virtualized memory in a nutshell. Did pretty good on time, it looks like today. We were at about around the time where I like to stay for these live streams, so I'm pretty good with it. So before we depart, the module content for this week is a little different. So I hope you all have an interesting and maybe a good time with that. It kind of changes the learning style just a little bit. So maybe you'll find it interesting. Maybe you'll find it easier. Maybe you'll find it harder. I'm not entirely sure which. If you have any questions, I'll be hanging out in the chat for a couple minutes, but also you can feel free to email me. Thank you again for watching, and we'll see you next time.